Some important carbon compounds. Almost all organic compounds are invaluable to us. Let us understand the importance of two such compounds. Ethanol. The common name for ethanol is ethyl alcohol or spirit. Ethanol is the second member of the homologous series of alcohols. The first member of the series is methyl alcohol. The formula of ethanol is C2H5OH. It is a straight chain compound and has a linear structure. Let us discuss the physical properties of ethanol. Ethanol is a colorless liquid with a pleasant odor. It has a low boiling point of 78 degrees Celsius and freezing point of minus 114 degrees Celsius. Ethanol is combustible and burns with a blue flame to form carbon dioxide and water. Let us discuss some reactions of ethyl alcohol. Reaction of sodium metal. Ethyl alcohol reacts with sodium metal to form sodium ethoxide and hydrogen gas. This is also a test for alcohols. The evolution of effervescence of hydrogen gas indicates that the given organic compound is an alcohol. Reaction with phosphorus trichloride. Ethyl alcohol reacts with phosphorus trichloride to form ethyl chloride and phosphorus acid. Dehydration of ethanol. When ethanol is heated with an excess of sulfuric acid at 444 Kelvin, it gets dehydrated to form ethane. Sulfuric acid acts as a dehydrating agent and removes a water molecule from ethanol. In this reaction, the hydrogen atom from the CH3 group and the OH group from the CH2OH group are removed to form water. This results in the formation of ethene, an unsaturated hydrocarbon. Uses of ethanol. Ethanol is used as an antiseptic to sterilize wounds and syringes in hospitals. Ethanol, being a good solvent, is used in medicines such as tincture iodine, cough syrups, and tonics. It is also used in the preparation of alcoholic drinks. Ethanol is also used as a fuel in cars along with petrol. Since it is a cleaner fuel and produces only carbon dioxide and water when burnt in sufficient amounts of air. Let us discuss the harmful effects of alcohol. If large quantities of alcohol are consumed, it slows down the activity of the central nervous system, due to which the judgment of the person is impaired and the reactions of the person become slow. Methanol, even if consumed in small quantities, can cause death of the person. Methanol gets oxidized in the liver to form methanal. Methanal reacts with the cells of the body, causing coagulation of the protoplasm. Due to this, the cells stop functioning normally, resulting in the death of the person. Methanol also affects the optic nerve, causing blindness. Ethanoic acid. Common name for ethanoic acid is acetic acid. Ethanoic acid is the second member of the homologous series of carboxylic acids. First member of the series is methanoic acid. The formula of ethanoic acid is C2H4O2 or CH3COOH. It is a straight chain compound and has a linear structure. Let us discuss the physical properties of ethanoic acid. Ethanoic acid is a colorless corrosive liquid with a pungent odor. Ethanoic acid, when dissolved in water, produces less hydrogen ions, hence it is a weak acid. At ordinary temperature, ethanoic acid is in the liquid state. When ethanoic acid is cooled below 290 Kelvin, it solidifies into an ice-like mass which looks like a glacier. Therefore, ethanoic acid is also called as glacial acetic acid or simply acetic acid. Let us perform an activity to compare the strength of ethanoic acid, a carboxylic acid, and dilute hydrochloric acid, a mineral acid. Take some dilute ethanoic acid and dilute hydrochloric acid in separate test tubes. Dip a blue litmus paper in each test tube. What do you observe? Both dilute ethanoic acid and dilute hydrochloric acid turn blue litmus paper red. This shows that both ethanoic acid and hydrochloric acid are acidic in nature, but the litmus test does not prove that ethanoic acid is a weak acid. Now, let us test both these acids using a universal indicator paper. Dip a universal indicator paper in both the acids. What do you observe? Dilute ethanoic acid turns the universal indicator paper orange, shows that the pH is about 4. Dilute hydrochloric acid turns the universal indicator paper to red, showing that its pH is about 1. This indicates that ethanoic acid is a weak acid. Hydrochloric acid is a strong acid. Carboxylic acids like ethanoic acid are only partially ionized in the solution to give a small number of hydrogen ions. They are therefore weak acids. Mineral acids like hydrochloric acid are completely ionized in the solution to give a large number of hydrogen ions. Therefore, they are strong acids. Reactions with chlorine. Acetic acid reacts with chlorine to form monochloroacetic acid and hydrogen chloride. Here, one hydrogen atom from the methyl group of acetic acid is replaced by one chlorine atom. Monochloroacetic acid further reacts with chlorine to form dichloroacetic acid. Here, one more hydrogen atom is replaced by the chlorine atom. Dichloroacetic acid further reacts with chlorine to form trichloroacetic acid. Here, the third hydrogen atom near the carbon atom is replaced by the chlorine atom. In this way, all the hydrogen atoms are replaced by the chlorine atoms. Reactions with sodium metal or zinc metal. Acetic acid reacts with sodium metal to form sodium acetate and hydrogen gas. Similarly, acetic acid reacts with zinc metal to form zinc acetate and hydrogen gas. Esterification. Acetic acid reacts with ethyl alcohol in the presence of anhydrous zinc chloride or sulfuric acid to form ethyl acetate and water. Ethyl acetate is an ester. This process is called esterification. This is also a test for carboxylic acids. The formation of an ester shows that the organic compound is carboxylic acid. Esters are sweet-smelling volatile liquids. They are used in making perfumes. They are also used in making artificial flavors and essences used in ice creams, sweets, etc. Hydrolysis of esters. When an ester is heated with sodium hydroxide solution, it gets hydrolyzed to form alcohol and sodium salt of the carboxylic acid. This process is called saponification, which is used in the manufacture of soaps. When ethyl acetate is boiled with sodium hydroxide solution, sodium ethanoate and ethanol are produced. Reactions with carbonates and bicarbonates. Let us perform an activity to understand the reaction between ethanoic acid and sodium carbonate. Take some sodium carbonate in a test tube and add about 2 ml of ethanoic acid. What do you observe? There is brisk evolution of a gas. Now, fix a bent tube and allow the gas to react with lime water. The lime water turns milky. This shows that the gas involved was carbon dioxide. Let us see the reaction. Ethanoic acid reacts with sodium carbonate to form sodium ethanoate, carbon dioxide and water. Similarly, ethanoic acid reacts with sodium bicarbonate to form sodium ethanoate, carbon dioxide and water. Reaction with sodium hydroxide. Ethanoic acid reacts with a base like sodium hydroxide to form a salt, sodium ethanoate and water. In this reaction, ethanoic acid behaves like a mineral acid and reacts with the base to form salt and water. Let's do a quick check. Soaps and detergents. When fats or oils are heated with either sodium hydroxide or potassium hydroxide, they form the respective sodium or potassium salt of the fatty acid along with glycerol. This salt so formed is called as soap, and the process is called saponification. Let us understand the structure of a soap molecule. The soap molecule has a tadpole-shaped structure. At one end of the soap molecule is a long hydrocarbon chain, which is hydrophobic or water-repelling in nature. This end is insoluble in water but soluble in oil or grease. At the other end of the soap molecule is the short ionic part of sodium carboxylate. This end is water-attracting or hydrophilic in nature and hence soluble in water but insoluble in oil or grease. When soap is mixed with water, the soap molecules form lather or they foam. The soap molecules cluster together to form spherical micelles called as soap micelles. When a dirty cloth is dipped in water containing soap, the soap particles and dirt come in contact with each other. The non-polar hydrocarbon ends of the soap molecule surround the oil or grease particles and begin to dissolve them. The polar carboxylate ions remain directed towards water. Thus, each oil or grease particle gets surrounded by a number of negatively charged hydrocarbon ends. The soap micelles trap the dirt particles which are attracted to the dirty cloth. Since like charges repel each other, the oil or grease drop breaks off and forms smaller grease droplets and gets dispersed in water. In this way, the oil or grease particles from the dirty cloth are removed, making the cloth clean. The purpose of using soap is to make oily or greasy particles mix with water so that they can be washed away during agitating and rinsing. Let us perform an activity to understand this. Take about 10 ml of water in 2 test tubes labeled A and B. Add a few drops of oil to each of the test tubes. Now add a few drops of soap solution to test tube B. Cork both the test tubes and shake them vigorously. What do you observe? In test tube A, the layer of oil floats above the layer of water. In test tube B, oil mixes with water to form an emulsion. From this activity, we can conclude that the presence of soap in water makes the oil mix with water. Let us prepare soap using vegetable oil, caustic soda and common salt. Take about 20 ml of vegetable oil in a beaker. Add to it about 30 ml of caustic soda solution or sodium hydroxide solution. To this solution, now add about 5 to 10 grams of common salt. Now heat the mixture with constant stirring till a paste of soap is formed. Common salt decreases the solubility of soap, because of which soap separates out from the solution. Stir the mixture well and allow it to cool. On cooling the solution, solid soap separates out. But there are a few limitations of using soap. Soap cannot be used for washing clothes in hard water. Hard water contains calcium and magnesium salts. When soap is mixed in hard water, most of the soap mixes with the calcium and magnesium ions of water to form an insoluble precipitate called scum. So a larger amount of soap is needed for washing clothes. This scum sticks to the clothes being washed, which makes the cleaning of clothes difficult. This difficulty can be overcome if detergents are used in place of soaps. Detergents are sodium salts of long-chain benzene sulfonic acids or long-chain alkyl hydrogen sulfates. These do not form insoluble calcium or magnesium salts in hard water and hence can be used for washing clothes even in hard water. Let us perform some activities to understand the action of hard water and soft water on soaps and detergents. Take about 10 ml of soft water, that is distilled water, and about 10 ml of hard water, that is water obtained from a hand pump, in separate test tubes. Add about 5 drops of soap solution in both the test tubes. Cork both the test tubes and shake them vigorously. We see that a lot of lather is formed in the test tube containing distilled water, and there is no lather formed in the test tube containing hard water. A white curd-like scum is formed in this test tube. From this activity, we can conclude that soap lathers easily in soft water and does not lather easily in hard water. In order to obtain more lather in hard water, more soap has to be added. Activity. Take about 10 ml of hard water in 2 separate test tubes. Add about 5 drops of soap solution to one test tube and about 5 drops of detergent solution in the other test tube. Cork both the test tubes and shake them vigorously. We see that no lather is formed in the test tube in which soap solution has been added. A white curd-like scum is also formed in the test tube. In the test tube containing detergent solution, a lot of lather is formed. This activity shows that soaps do not lather in hard water, while detergents lather in hard water. Would we be able to check whether a sample of water is hard by using detergents? Since detergents lather easily in soft water as well as hard water, hence we would not be able to check whether a sample of water is hard by using detergents. We use laundry soaps or detergents for washing clothes as they are better cleansing agents than bath soaps. Bath soaps use high quality fats or oils as raw materials as compared to the fats and oils used in laundry soaps. We have also experienced that expensive and better quality perfumes are used in bath soaps as compared to those used in laundry soaps. Bath soaps do not harm the skin, as the manufacturing processes used in bath soaps ensure that there is no free alkali content present in them. Such care is not taken in the manufacturing processes used in laundry soaps. Hence, it has been observed that most laundry soaps are harmful for the skin. Let's do a quick check.